Next we will calculate what is the magnetic field of a dipole. The magnetic field at any point P at an angular position theta at a distance r from the center of the dipole, we can resolve this into two components. One component is along the line, that is B radial along the radius vector direction BR. Another component perpendicular to this is B theta. The resultant of these two will be equal to the magnetic field B. The magnetic field at any point at an angular position theta at a distance r from the center of the dipole can be obtained by resolving it into two components. One component BR is along the radius vector and another component B theta is perpendicular to radius vector. So first the radial component of the magnetic field BR we can calculate. What will BR equal to? Minus dV by dr. That means if I take the dipole line like this is theta component, this is point P, this is dr component. Whereas if we take in this direction, then this will be r d theta component. This angle here is d theta. So when you take dr, dV by dr in this direction. So minus d by dr times of the potential. That we know, we have calculated mu naught by 4 pi m cos theta divided by r square. So let us differentiate this value. We are going to get this one as mu naught by 4 pi 2m cos theta divided by r cube. This is the magnetic field along the radial direction. Now along the direction theta, dV by dr, that is dV by r d theta. So magnetic field along theta minus dV by dr, that also can be written as minus dV by r d theta. So that can be taken as minus 1 by r dV by d theta. So minus 1 by r d by d theta of V. What is V? We know mu naught by 4 pi m cos theta divided by r square. So this can be written as mu naught by 4 pi, differentiating capital M by r square, you can take it constant, 1 by r square, and r this becomes 1 by r cube d by dt of cos theta. So we are left over with m sin theta divided by r cube. So now this is B theta. We have with us B theta and BR. What is the resultant field? The resultant field B is equal to under root of BR square plus B theta square, because these two components are perpendicular to each other. Let us substitute this value. Magnetic field B will be mu naught by 4 pi m by r cube can be taken constant. Under root of 2 cos theta whole square plus sin theta whole square. So 2 cos theta whole square, that is radial direction, plus here we have sin theta whole square. So this can be written as 4 cos square theta plus sin square theta. One of the cos square theta plus sin square theta is 1. So remaining will be mu naught by 4 pi m by r cube into under root of 3 cos square theta plus 1. This is the magnetic field at any point. This is the magnetic field at any point at the angular position theta. Magnetic field at any point at the angular position theta. Now we want to calculate the angle made by the resultant. The resultant magnetic field is in this direction. So this angle here is equal to say alpha. So this total angle will be theta plus alpha. Let this makes an angle alpha with the radius vector r. This is the radius vector r. So what will be tan alpha? Tan alpha will be B theta by BR. Tan alpha, to give the direction, it is B theta by BR. So B theta by BR we have to substitute. B theta is m sin theta by r cube mu naught by 4 pi. BR will be mu naught by 4 pi 2m cos theta by r cube. So we are left over with tan theta by 2. So tan alpha will be direction point of view. It is equal to tan theta by 2. Tan inverse of tan theta by 2 will be the angle the magnetic field is. Now let us take some special cases so that we can understand how is the potential and magnetic field lies. Suppose I take case 1. We want to take magnetic field of dipole on the axis of dipole. On the axis of dipole means here we want to calculate. Here what will be theta? Theta can be taken as equal to 0 degrees. So along this point what will be potential now? V is equal to mu naught by 4 pi m cos theta by r square. So cos theta, theta value substitute as 0. So it will be mu naught m by 4 pi r square. What will be the magnetic field at this point? It will be mu naught by 4 pi 2m cos theta by r cube, that is Br. B theta will be mu naught by 4 pi m sin theta by r cube. Sin theta, theta 0 means will be 0. So magnetic field will be remaining mu naught by 4 pi 2m by r cube. What will be angle alpha? Tan alpha is equal to tan theta by 2. Theta is 0. So here alpha will be also equal to 0. So the magnetic field will be in this direction, and this magnetic field we can call it as along axial line as BA. Mu naught by 4 pi 2m by r cube, where r is the distance from center to this point. This is an axial point. And the direction, since alpha is equal to 0, the direction of the magnetic field is from south to north along the axial line. Now let us see the case 2. On the equatorial line or equator of the dipole, that means theta is equal to 90 degrees. So we know the potential formula. V is equal to mu naught by 4 pi m cos 90 divided by r square. So it is equal to 0. So potential at that point is equal to 0. Magnetic field along equatorial line, let me put it as BE, mu naught by 4 pi into 2m cos theta by r square. So this 2m cos theta will be 0. So left over will be only sin theta term. M by r cube. This is the magnetic field along the axis. And tan alpha is equal to tan 90 by 2. So alpha will be equal to 180 degrees. That is this direction. This is the magnetic field along equatorial line, parallel to the axis as if from north to south pole. Whereas along the axial line, it is along the axis as if from south to north pole. Here it is from north to south pole. This is the direction of magnetic field along the equatorial line of the bar magnet. So magnetic field we can take as we studied the case 1 and case 2. We can also use the formula what we have derived earlier with respect to the r and length L. So in the case 1, we will take on the axis of the magnet. We'll call this position as called end on position for a magnet of length L. B will be equal to mu naught by 4 pi 2mr divided by r square minus L square by 4 whole square. For L is much less than r, the magnetic field along axial line is mu naught by 4 pi 2m by r cube. Similarly, case 2, on the equator of the magnet, we can also call this as broadside on position. B is equal to mu naught by 4 pi capital M divided by, you have left over with r square plus L square by 4 to the power 3 by 2. For L is much less than r, we can neglect L square by 4. Then we get magnetic field along equatorial line as mu naught by 4 pi m by r cube. Magnetic field along end on position is twice the magnetic field along broadside on position for the same distance.